balanced chemical equations, and I'm going to start down here where it says the use of chemical shorthand. Okay, so in 1774, Joseph Priestley performed a pretty famous chemical reaction that led to the discovery of oxygen. And what he did was he heated a deep red powder, and that deep red powder was mercury 2 oxide, which is HGO. And when he heated it, it produced a liquid, and that liquid was silver, and then a clear odorless gas. So he produced mercury and oxygen. Okay, so mercury is Hg, and then oxygen is diatomic because it's pure, so it's O2. There are two different ways to represent this chemical reaction. One is called a word equation. That's where everything is written with the chemical names. And the other one is the formula equation, where you have all of the chemical formulas written. And then sometimes if you know the state of matter, it would include the state of matter. Okay, so formula equations are sometimes referred to as molecular equations. Okay, and the substances that you start with, those are called the reactants. So the starting substances are the reactants. So here, HGO would be my reactant. It's on the left-hand side of the arrow. And then the new substances that you form are called the products. So that would be the mercury and the oxygen gas. Okay, sometimes you may see italicized letters, and typically the italicized letters are going to be the states of matter. So like this solid is in the parentheses is the little S italicized, this script L, this is liquid, and then this G is gas. Okay, let's take a look at the top of the next page. So at the top of the next page, they just reiterate the states of matter that I just talked to you about. So solid is typically a little S in parentheses, liquid is often a script L in parentheses, and gas is a little G in parentheses. Now, if something is dissolved in water, it's AQ, which is aqueous. Okay? Now, in terms of the chemical reaction that we were talking about on the previous page, in this figure, they're showing you what it looked like. So here they've got that red solid mercury 2 oxide that's being heated in a Bunsen burner. And then as it's heated, you're producing liquid mercury, and then oxygen gas would be released from that test tube. Okay? Now, you don't know it yet, but there is a form of evidence, a couple forms of evidence here that a chemical reaction is happening. So this unexpected color change from red into this silvery color, that's one form of evidence that a chemical reaction occurs. Another one is that a gas is produced. So let's come down here to the different forms of evidence, and you definitely want to know these. These are things that I will ask you about either on a lab or on a test. So the examples of a chemical reaction occurring would be when something absorbs heat. So that means it will feel cooler to touch. Okay. The other one would be it releases heat. So it will feel warmer. That means you've mixed things together, let's say in a test tube, and you're holding it, and that test tube suddenly feels warmer or it feels cooler. This release of heat has nothing to do with your heating it with a Bunsen burner. Okay. Sometimes it'll release light, an unexpected color change. So if you mix two things like yellow and blue, you would expect it to make green. That is not an example of an unexpected color change. That's expected. If you're mixing things together and then suddenly it turns gray, like they were colorless and now it's gray. Okay. Evolution of gas. This simply means gas is being produced. So if you have a solution, you're mixing things together, and you see little tiny bubbles forming on the inside of a test tube, that would be a gas is forming. And then the last one would be forming a solid from two solutions being mixed. The solid would be known as a precipitate. Okay, this typically occurs when you mix two solutions together. It'll appear cloudy, and then eventually it will settle to the bottom, and that solid is your precipitate. Okay, precipitates could be many colors. They could be white, black, gray, yellow. It just depends. Okay, let's move on to balancing chemical equations. So balancing chemical equations is necessary because we have to follow the law of conservation of mass. So that means I have to have the same number of each type of atom on the reactant and the product side. So this is how we do that. We will be changing coefficients or numbers in front of chemical formulas. You will not be changing subscripts because subscripts would change what the substance actually is. So let's take a look at the next page. And let's practice balancing chemical equations. So I'm going to highlight this word coefficient before we practice some. So these coefficients are the numbers that go in front of the chemical formula, and those coefficients go to every atom immediately after it in the chemical formula. Okay, so let's take a look at the next page here. Okay. All right, I'm going to go through and I'm going to highlight everything just to make it easier to see. So in A, I have one sodium on each side, okay? Then, if you look at chlorine, we have two chlorines on each side, agreed? Because there's a subscript 2 on each one. So since I don't have to do anything here, everything is already balanced. That means there is a 1 coefficient in front of every substance, okay? You don't have to show the number 1. It is assumed it is there if you don't write it. Okay, it's your choice whether you decide to write it or not. Let's go to B. In B, I have 1 silver on each side, okay? I've also got a polyatomic ion on each side. So you balance polyatomic ions as groups. NO3 is the nitrate ion, okay? So I'm going to group that together, and I'm highlighting the whole thing because I have 1 of each nitrate on either side. Then I have a potassium on both sides, and then I have a bromine on both sides. So this is technically already balanced as well. So that means I have 1s in front of every substance. Okay. When I look at C, I'm going to highlight the hydrogens. And you want to be careful here because I have a 4 in front of HCl on the product side. This coefficient will get distributed to the hydrogen and the chlorine immediately after it, okay? So if I've got 4 hydrogens on the right, but I've only got 2 hydrogens on the left, I need to put a 2 in front of H2O because 2 times 2 would give me 4. So now my hydrogens are balanced, okay? Now this 2 that I just added will also go to the O immediately after it in the chemical formula. How many O's do I have on the product side? 2. So now my O is balanced, okay? Next, I'm going to highlight the silicon. I've got a silicon on each side, okay? And then I'm going to highlight the chlorine. I've got 4 chlorine on the left. And don't I already have 4 chlorine on the right because of this coefficient in front of HCl? So that means we're balanced. So this is 2, 1, 1, 4. Okay? If you're doing a multiple choice question, I'm asking you which of the following coefficients will balance the equation, then you will often see these coefficients written in a row, like 2, 1, 1, 4. Okay? All right. Let's take a look at D. I'm going to highlight the carbon. I've got 3 on the left. How many carbons do I have on the right?
3.
Yeah, 3, because there's a coefficient of 3 in front of it. Now I'm going to highlight the hydrogen. I have 8 hydrogen on the left. How many hydrogens do I have over here on the right? 8, yeah, because 4 times 2 would be 8 hydrogen. Then I'm going to go ahead and highlight my oxygen. Now, my oxygens are split up on the product side. I have oxygen in 2 separate compounds, okay? So that means we would add them up. So here on the left, I've got 10 oxygen. And then over here on the right, I have 6 here plus 4. So 6 plus 4 is 10, so that means we are balanced. So my coefficients are 1, 5, 3, 4. Does this make sense? Okay. I think you get the idea. I'll do one more, and then I think it's time for you guys to practice it. So if you take a look at E, on E, I've got 3 lithium here, and then I have 3 lithium over here. And then hydroxide is a polyatomic ion. So I'm highlighting the hydroxide all together. On the reactant side, I have 3 of these hydroxides. On the product side, I have 3 hydroxides. I have 1 iron here. I have 1 iron here. And then I'm highlighting per iodate, which is IO4, all in one color, because that's also a polyatomic ion. Here it's in parentheses, so I have 3 IO4s, and over here I have 3 IO4s. So my coefficients are 3, 1, 1, 3. Yes? Okay. Let's see if you got it. Let's go to the next page. I want you to do number 2. You may need to rewrite number 2 with some blanks in front of them. What I mean by that is you may want to write 2A. So it looks like this. Have a space in front of each substance. And I would do this in pencil. So that way you can write the coefficients in the spaces. Okay? So work with the person next to you and let's see what you come up with. You can start wherever you want. I tend to start in certain places just because I've been doing this a long time. Okay, so I've got 3 SO4s over here. So that means I would probably put a 3 here to balance the SO4. Then that changes how many hydrogens I have. Now I've got 6 hydrogen. So I would put a 3 here to balance the hydrogen. And then you've got 2 aluminums on the right, so I would put a 2 here. So it's 2, 3, 1, 3. Did you get that? Yes. Okay, awesome. Let's take a look at B. In B, what I might do is I would probably rewrite water as HOH and balance it as a hydrogen attached to a hydroxide. What I mean by that is I've got 2 hydroxides here, but then I've got 3 hydrogens here. So the lowest common multiple of 2 and 3 is 6. So I might put a 6 here, and I'm just playing with it. So I'm just showing you how I do it. If I put a 6 here, 3 times 2 is 6. I put a 2 here, 2 times 3 is 6. Now that gives me 2 nitrogens, which I already have. And then don't I already have 3 magnesium on each side? So 1, 6, 3, 2 would be my answer. Okay, and then for 2C, I probably, again, since I have 3 hydrogens here and 2 hydrogens here, lowest common multiple is 6. I would put a 2 here. 2 times 3 is 6 hydrogen. 3 times 2 is 6 hydrogen. Then I've got 2 nitrogens. I'd put a 2 here, 2 nitrogens. And then I always balance the lone element last. So I've got 3 oxygen here and 2 here. 3 plus 2 is what? 5. Okay, so here's a little trick. Put the odd number that you want. This works with O2. Put the odd number that you want in front of the O2. Because if we just had an O there, would we be done? Okay. But since it's 2, if you double the other coefficients, you'll be done. This is 4. This is 6.